Hi everyone, welcome to the second semester of algebra. My name is Sveta Makarova and I will be your lecturer for this semester. Let us start with defining the main object of study, a ring. So, a ring R is a set with two binary operations. They are called addition, denoted by plus, as you can expect, and multiplication, denoted by a dot. And they are subject to the following axioms. So, first, we want the set R to be an abelian group that is for every two elements, A and B in R, A plus B is equal to B plus A. Also for every triple of elements, we have the associativity condition, A plus B plus C. There exists the identity with respect to addition, and it is usually denoted by 0. So we say that there exists an element 0 in R such that for every other element A in R, A plus 0 is equal to 0 plus A is equal to A itself. And we want to ensure the existence of additive inverses. So for every element A in R, there exists A prime in R such that A plus A prime is equal to 0. So this element A prime, the additive inverse, is denoted by minus A. And then we want to formalize the interaction between addition and multiplication. So we say that multiplication is distributive with respect to addition. So for every triple A, B, and C, A plus B times C is equal to A times C plus B times C. And similarly, A times B plus C is equal to A times B plus A times C. So this is called distributivity You may notice that these properties are very familiar to you, and that is why we say that the notion of a ring formalizes the notion of a number system. So when we say a ring, it is a very scientific word for saying a number system. And as our first examples of rings, so hopefully Z is a very familiar example. So it is the ring of integers. Also, we have Q, rational numbers, the real numbers are complex numbers. We have Q as well as real numbers R and complex numbers C. Excuse me. I hope you won't mind my cat appearing sometimes in the videos. Her name is Victoria Waldhausen. Okay, back to the rings. We can also form rings of polynomials. Denoted by z square bracket x or c square brackets x and y. This is the ring of polynomials in two variables. And let's say that we also have the ring of matrices n by n, with coefficients in, for example, R. This set forms a ring, but we can notice that it is, in a sense, different from all the rings, all the examples above, because when we multiply two matrices, they do not necessarily commute, whereas when we multiply numbers, their multiplication is commutative. And this motivates the following definitions. What kinds of rings can we study? Let us fix the notation for now. Let R be a ring. You might have noticed that the only axiom that I introduced for multiplication was distributivity, namely the interaction between addition and multiplication. But we could have asked that multiplication is associative. And in this case, we say that a ring R is associative if multiplication is, that is, for every triple A, B, and C, A times B times C is equal to A times BC. So, why do some people not assume that the rings are associative? Well, because you have already worked with non-associative rings. So, for example, let us take R cubed with basis vectors I, J, and K. Then R is not associative. Under the cross product. So for example, when we try to multiply I by j and then by j again, we can see what happens. Or when we first multiply j by j and then by I on the outside and see what happens there. So an easy way to remember how to multiply these basis vectors is to draw this carousel and see if we multiply two vectors in succession. So for example, we take, I wrote dots again. So let me correct this. Cross, 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 and cross. So here we multiply I by j and we first write I and then j. So we follow this arrow and the result should be k according to this mnemonic rule. So we get k times j. Here we multiply k by j, but we go in the opposite direction. So we acquire the minus sign and we get minus I. What happens here? When we multiply two parallel vectors, their cross product is 0. And then multiply anything by 0, we get 0. And minus I is not equal to 0, therefore we can say that this ring is not associative. This ring is a particular example of the Lie algebra, and people study them extensively, but we will not touch upon them in the course. So after this lecture, all the rings will be associative. What else can we say about our rings? R is unital if there exists multiplicative identity. This element is usually denoted by 1 or 1 subscript r, and it satisfies the following property. So for every a in R, 1 times a is equal to a times 1 is equal to a. So multiplying by 1 does not change the element. In particular, one times 1 is should be equal to 1. And so we can see again that R cubed with the cross product is not unital. But also, if we consider the set of even integers, denoted by 2z, even integers. This is also not a unital ring. And this is a nice example to think through on your own. So try to think if there was an identity, then identity times identity would be equal to itself. And you can see that in these two examples, there is no such element. So I will ask you to explain this to me when we meet. The next definition is, we say that our ring R is a commutative ring. I think I need to check up on my head. We say that our ring R is commutative if multiplication is commutative. It means that for every pair of elements A and B inside R, A times B is equal to B times A. And let us consider some examples. So first, non-examples. R cubed with the cross product is not commutative, but it is anti-commutative. In the sense that A times B is equal to minus B times A. But let us not talk about it further. So another non-example is the ring of matrices, n by n matrices over basically any field, but let us write R for n greater than 1. Because if n is equal to 1, then it is just R, and R is commutative. And when n is at least 2, then we can come up with examples of two matrices that do not commute. Okay? And for real examples, ring of integers, also your familiar fields, QR, etc. The non-unital ring 2Z is still commutative because it inherits its operation from the ring Z. It is in fact a subring, and Z is commutative. And the ring of numbers modulo n, in particular, let's say Z mod for Z, then this is a ring consisting of 4 elements, as element 0, element 1, element 2, and element 3. And the operations are, as you can expect, 1 plus 1 is equal to 2, 2 plus 1 is equal to 3, but then 2 plus 2 is equal to 4, and the class of 4 is identified with the class of 0, so 2 plus 2 is equal to 0. And then 1 plus 3 is also equal to 0. And when we multiply, we do the same. We identify numbers that differ by 4. So 2 times 2 is going to be 0. And 3 times 1 is 3. 3 times 2 is 6. So modulo 4, it will be equal to 2. And 3 times 3 will be equal to 1. So basically by going over each element, we can see that this ring is commutative. But we will see later that in fact quotient rings and this operation can be generalized to arbitrary rings. Quotient rings of commutative rings will also be commutative. Okay, so for the remainder of the course, all of our rings will be assumed unital, associative, and commutative, unless specified otherwise. But even if we work with non-commutative rings, they will at least be unital and associative. Now, R is a ring, which is from now on is assumed to be unital, associative, and commutative. And we say that a subset S inside R is a subring if the restrictions of both operations define a ring structure on S. And in addition, we want that the multiplicative identity of R is contained inside S. Since all of our rings are assumed to be unique. Let's consider some examples. So Z is a subring of Q, and Q is a subring of R, and R is a subring of C. And a non-example. The set consisting of 0 inside any ring if the ring itself is non-zero. If R itself is non-zero. And this is precisely because the identity is not inside this zero ring, although zero itself is a unital, associative, and commutative ring. And in fact, it is my favorite example of a ring. Now we move on to the properties of elements inside the ring. So, definition, we say that an element U inside R is a unit, not to be confused with identity. If there exists its multiplicative inverse. If there exists U inverse inside R, such that U times U inverse is equal to U inverse times U is equal to identity. And we say that our ring R is a field F R is not zero and all non-zero elements are units. So, for example, Q, R, and C are fields, and we will discuss it later that Z mod a prime number P is a field too. If P is prime. We denote by R cross the set of all units of R. So for fields, R cross coincides with R minus 0. To end this lecture on a high note, I am going to prove two propositions. So first, multiplying by 0 yields 0. So you can say that 0 is multiplicatively absorbing. If you want to be able to say it in very long words. So let us prove it. Okay, so 0 times A is equal to, we can write 0 as a sum of 0 and 0, because 0 is the additive identity. Then by using distributivity we get that this is equal to 0 plus 0 times A plus 0 times A. And by moving one of the summands to the left, so we can subtract 0 times A from both sides. We get that 0 to 0 times A minus 0 times A. This is equal to 0 times A. So 0 times A is equal to 0. And another property that you really want to have handy for the future is the following: that finding additive inverse is the same as multiplying by -1. So for every element in R, minus A, the additive inverse, is equal to -1 times A. This is, by the way, a trick from calculus classes, writing 0 as a sum of two non-zero elements, or in this case, sum of two zero elements. So we write 0. 0 is equal to 0 times A. And this is equal to 0 is equal to 1 plus -1. So we're taking the additive inverse of identity here. We know that they should sum up to 0. Therefore, we were able to do this transition multiplied by A. And then we use distributivity, so we get that 1 times A plus -1 times A. And we know that we use the property of the multiplicative identity to write 1 times A as A. So we have A plus -1 times A. And so A plus something yields 0. Therefore, this something has to be the additive inverse. Has to be additive inverse, which is denoted by -A. And this is how we prove this proposition. With this, I hope you now have an idea of what sort of objects we are going to work with, and I hope that you're going to solve the exercises and explain them to me either on Wednesday or on Thursday.